Okay, so what we're going to do is work on these problems. We're actually going to be able to get through all 8 of them. But what I want to do today is I want to concentrate on, you're going to see that giving you just 1 to 2 sentences, we can actually convey a lot of information. And when you're doing these word problems, it's very important that you know how to draw the scenario that's being described and that you're labeling the information they've given in the right place. And you'll see that the math is actually the easiest part. If you can get the picture and have a good visual, you'll see that the calculations we're going to do today are actually not bad at all. So what we're going to be focusing on is right triangle trig and acute angles. And so we're going to be looking at our 6 trig functions and sectors of circles. And we want to make sure that we can find everything we need. So it's sort of a game of finding right triangles, because in order to work with those 6 trig functions, we have to find a right triangle. So it's a little bit geometrical too. So the first question that I want to look at, and by the way, you better believe we're going to give you problems where we're just going to describe a scenario and you're going to have to draw a picture on your own. So sometimes the diagram will be provided for you, but one of the skills we want to make sure you get out of this class is being able to draw the sketch. Okay, so the first one's an equilateral arch, and it's drawn around an equilateral triangle. And each side of the triangle is going to have side length 10. And it says, for example, arc AC is a circular arc having center B. And we want to calculate the area and perimeter of the arch. Or arc, excuse me. Arch. That's right. Yeah. So what's going to happen here is this is not like a semicircle, right, that we're drawing. What we actually are going to have is an equilateral triangle. And every side of the triangle is 10, right? Notice they didn't give us any angles, but they don't have to, because we know that all the angles inside the triangle, here you go, all the angles inside the triangle are equal, and since all the angles add up to 180, each one of these, right, is a 60-degree angle. Now, the arch works the following way. So what's happening is these 2 sides of the circle are going to make, right, a piece of a circle, and then these 2 sides are going to make another piece of a circle. So these are 2 sectors that are kind of overlapping. So what you're getting is a curved archway, but it's not a semicircle, okay? So in order to figure out the perimeter of this guy, well, the perimeter is we're going to add the sides. So the triangle's just in here for reference. The arch is actually this outside stuff. So if this is going to have arc length S, by symmetry, this is also going to have arc length S. So if we want to figure out the perimeter, well, we're going to have 2 sides of length S and 1 side of length 10 at the bottom. We don't actually know the arc length, but we can calculate it using the formula we learned in, I think, section 1, which is S is R theta. So we can replace S in our formula, right, with R theta. So the R is easy. The R is 10, right, because that's going to be what the sides of the triangle make up the arc, or the sector, excuse me. And the angle is 60 degrees. But when you calculate arc length, you have to use radians. So if we want to convert 60 degrees into radians, right, we know that 180 degrees is pi radians. Degrees are going to cancel, and so our angles are pi over 3. And if you try to put your calculator in degree mode and just say I'm going to plug in 60, it's not going to work, because the calculator doesn't recognize the 60 degrees unless it's inside of a trig function, okay? So you would have to convert this to radians. So our perimeter is going to be 2 times 10, right, times pi over 3 plus 10. And this is your exact answer. To calculate the area, well, what's going on here is these 2 sides of the triangle make up a sector of a circle. So we can calculate the area of that particular sector. And we actually have 3 options, right? We can say, well, we can calculate it using 1/2 RS. We can do 1/2 R squared theta. or we could do 1/2 s squared over theta. But since I don't know what s is, we know r and theta, it's going to make sense to use this version of the area formula. So if I want to calculate the area of the sector I highlighted, it's going to be 1/2. Our r was 10, so we'll square that. And once again, I have to use the radian measure of my angle. Well, this only got us the area of part of the arch. We're missing this piece, okay? And in order to get that piece, well, that lives in this sector of the circle. So I can add that area of that sector, and it's also going to be 1/2 10 squared times pi over 3. But is this the final answer? No. Why? What's wrong with it? Well, we could simplify it, but what did we actually just calculate? We calculated the two areas of those overlapping sectors. So my question is that equal to the area under the arch? No. Why isn't it equal to the area of the arch? Yeah, we counted the triangle twice, right? So that triangle was inside each of those sectors. So when we calculated the area, we actually put the triangle in twice. So if we back out, right, or subtract off the area of the triangle, that will give us the actual resulting area of the arch. Now the issue is here, this is a triangle, but it's not a right triangle, right? So typically when we want to calculate the area of a triangle, we're going to do 1/2 base times height. And the only kind of method you've learned to do that, use up till now to do that, is we would have to divide the triangle in half to find h, do the Pythagorean theorems, kind of like what we did on the equilateral triangle to derive the special angles. But there's actually another easier way we can calculate the area of a triangle. So for any arbitrary triangle, right? So I'm going to do something like this. This is not an isosceles triangle. This is not a right triangle, right? This is just any random triangle. If we wanted to calculate the area of this guy, we would take the length of the base, right? We would find the height, and we would say 1/2 base times height. So let's label the other two sides of this triangle. If you know one of the interior angles in the triangle, so for example, if we know the value of that angle right there, well, if I wanted to find height h, I can now use trigonometry to do that. And I could say, well, if this is theta, this right triangle on the left, this is the opposite side, this is the hypotenuse. So sine of theta is h over a, so a sine theta is h. So now, if you take your formula, 1/2 base times height, and plug this in for h, and the only reason I put the a in front of the b is we just usually alphabetize the variables. If they're in the formula, that's it. That's the only reason I did that. We now have an alternative formula for finding the area of any triangle, okay? The condition, though, to use this is you have to know two of the sides of the triangle, and you have to know the angle between those two sides. And so that's what we had here. We had side A, we had side B, and we knew the angle between them. So if you're ever in a side angle side situation, you can calculate the area doing this. So if we come back up here and we say, well, minus B was 10, A was also 10, so it gets squared, sine pi over 3. So there's nothing that says I couldn't say sine of 60, but since we've already used the radian measure and the other theta in the formula, it would just make sense to keep things in radians. So if you had written sine 60 degrees there, that would also be okay. It's just you would have to make sure that your calculator was in degree mode if you wanted to actually compute this out. So this is the exact answer for the area of the arch. So this is the kind of game you're going to have to play when you're dealing with random shapes, you want to break it up into recognizable geometric shapes, and you just want to make sure when you're calculating the area that you're getting all of it. And there really was no way for me to just get this little, almost looks like an ice cream cone, there was really no way for me to get the scoop, right, without grabbing the whole cone, because we know the area of a arc of a, or sector of a circle. We don't have a method to calculate the area of just that. Yeah.
Why is the 1/2 negative?
It's because I'm subtracting it, right? So the first, the red stuff got the triangle, right? The green stuff got the triangle, so we grabbed it twice, and then the light green is subtracting out one of the triangles. So now we have the true area of the arch. Make sense? Okay. All right, so let's look at the next one. In the next problem, right, we have a ladder that's 24 feet long, and we've leaned it against the side of a building. So here's our building. And the ladder is just leaning across like this, okay? The length of the ladder, which is 24 feet, the ladder is the hypotenuse of this right triangle that we've just created, all right? And they've told us that the angle between the ladder and the building is 25 degrees. So you have to make sure that you're putting the 25 in the right place. So the ladder in the building, they're describing the upper angle. If they said the ladder in the ground, that would be describing the lower angle. So now they want us to find the distance that the base of the ladder is from the base of the building. So we want to find that value x. So once you've drawn your picture and you found your right triangle, you always want to make sure that you have an angle inside the triangle, which we do. So then you hone in on the angle first, and then we say, well, which two sides do we know about or are looking for? So in this case, x is the opposite side to that angle. 24 is the hypotenuse of the triangle. So sine is opposite over hypotenuse. So sine of 25 degrees is x over 24, and now you just solve for x. So 24 sine 25 degrees equals x. And if I gave you guys this picture, everybody would get that right pretty much every time. If I give you a description of the picture, right, the trick is drawing it and putting everything in the right place. Now, if you're doing a problem on the exam and we ask you to generate your own picture, if you just wrote the math down and didn't sketch a picture, right, you're kind of setting yourself up, because if you're right, well, that's great. But if you're wrong, you're not really leaving yourself any options for partial credit. But if you drew the diagram and then just maybe labeled the angle wrong, well, that would be a minor deduction, because I'd have to get you for not, because it was described, you didn't get the description right. But then if you correctly did all the math based on your wrong picture, right, you're really opening yourself up for a lot of partial credit. So the biggest mistake people make when we're doing problems like this is they don't sketch a diagram and they don't label things clearly on the diagram. But a very clearly labeled picture, you would be surprised how far that will get you. And it will also wipe a lot of the mystery out of the problem of what to do. All right, so the next problem is a continuation of this one. And so what we're going to do now is we're going to take that same ladder, but we're going to slide it in such a way where the base of the ladder is slid 2 feet to the right. So now what the ladder is going to look like is something like this. It's still 24 feet long, but now the distance is the original x plus the 2 feet we move the ladder. And what this question is asking is how far down did the top of the ladder go? So we don't want to know what the height of this triangle is. I want to know what the difference is. So if we come back to the previous problem and I label the height of the original triangle y, well, y, right, is right here at some point above, because if you slide it, because the ladder has fixed length, right, if we slide the base this way, the top of it's got to slide down, okay? So what I need to figure out is, right, what's that little gap right there that it fell down? So I'm just going to label the new height A, and I'm just picking a letter out of the alphabet. So what I want to find is that little distance D right there, right? And D is actually going to be y minus a. So if I can find y and I can find a, I just need to calculate the difference, and that'll give me how far the ladder slid down, right? So getting a or y is actually pretty easy. So if we go back to the original problem, well, y is the adjacent side. We're still going to use the hypotenuse. So instead of using sine, we just change it to cosine. So 24 cosine 25 degrees is going to be the length of y. But when I calculate a, I have to use a different method because I don't know what any of the interior angles are. I know that I've still got a right angle, so I can use trigonometry if I had one of the other angles, but that doesn't tell you anything about the measure of the angle. Now, I know that when I slid the ladder this way, the way I did it, I know this angle got smaller, and I know this angle got bigger, so I know it's more than 25 degrees, but I don't know what the value is. So when you don't have any of the angle measures, that's when we have to revert back, and the only thing we have is the Pythagorean theorem, right? Because we have all three sides labeled. So I can actually solve for a using the Pythagorean theorem. So a squared, right, plus x plus 2 squared is going to equal 24 squared. If we solve this for a, right, we need to move the x plus 2 over to the other side. And then a, right, is going to be the square root of all this stuff. So the reason I haven't plugged in the 24 sine 25 for x was because I knew I needed to do several lines of algebra, and I didn't have to write that out again and again and again, okay? So one of the solving techniques you can do is, remember, there's no need to just plug all the values in until you need them. So, you know, do the algebra and then wait and plug all that stuff in at the end when you're done. So if we want to calculate d, right, it's y minus a. So d is going to be y, which was 24 cosine 25 degrees, minus a, which was the square root of 24 squared, minus, now I'll plug in what x was. X was 24 sine 25 degrees, right? We still have our plus 2 quantity squared. And so now we have the difference of those two values, and if you put this into your calculator, it's just a little bit more than 1 foot. It's like 1.04 feet, so it's about a foot is what the ladder slid down. But this is your exact answer. So we can only use the trig if we actually know an angle. And you can't assume, right, that the angles were the same. They definitely would have changed. Does everybody understand why the bottom angle got smaller and the big angle got taller? Okay? And so if you just kind of look at the ladder, right, it just, when we slid it down, it did this. So clearly that angle got smaller, and if that angle gets smaller, the other one has to get bigger because they always have to add up to 90, right? All right, any questions on this? No? It's Friday, everybody's tired. Okay, so let's look at this next one. I really like this problem. So in this one, it mentions there's a picture, but there's no picture. We can actually draw this without, just based on the description. So what we have is a drawbridge that's 100 feet long, and it's stretched across a river. And it says the two sections of the bridge can be rotated upward through an angle of 34 degrees. So when you think of drawbridges, we kind of think of like the old school medieval ones, which are just one big piece of wood that you draw up, right? But this says the two sections. So if we're talking about a river or a waterway, right, we actually split the bridge in half and we lift the two sections each. So what it's saying is when we lift the sections up, they only lift to 34 degrees. So when we draw this, and part A says that the water, right, is 5 feet below the top of the bridge. So when we draw this, we're really looking, right, at something like this. So 5 feet, 5 feet, there's the river, and the bridge has a total span, right, of 100 feet. So when the bridge is closed, we would just have a flat line across the top. But when we open the bridge, it's going to look something like this, and the angle it makes with the horizontal, right, is 34 degrees. And that's the same on each side. So how long is each piece? $50, right? When they close, they're 100. You're going to split it in half. You're not going to have a drawbridge where one's 25 and one's 75. That doesn't make any sense, right? So these are just going to be 50. So there's two parts to this question. Part A wants to know, well, how far is it from the top of one of these pieces all the way back down to the water? And part B wants to know, well, how wide is the opening at the top, right? So we need to find some right triangles. So to do part A, we're actually calculating this total height. So I can use that little right triangle that I've created at the top, and the height of the triangle, right, we'll call it y. So the height to the water is y plus 5. So once you have the height of the triangle, we know it's another 5 feet down to the water. So if I figure out what y is, I just plug it into there and I'm done, right? So if we look at that triangle, well, y is the opposite side to our angle. 50 is the hypotenuse of that triangle. So opposite over hypotenuse is sine. So sine of 34 degrees is y over 50. So 50 sine 34 is y. So that means the total height of the bridge down to the water is 50 sine 34 plus 5. If we want to measure the width of the opening, right, I'm going to call that D. So we need to know, well, how wide of a ship can fit through this opening when the bridge is open, okay? So if we look at this, well, I've got two triangles on each side, right, of equal size. If we call the base of the triangle X, well, then look what should happen as we go across. X plus D plus X should add up to 100. So X plus D plus X is 100. Since D is what we're looking for, simply subtract the X's from both sides. So we need to figure out what 100 minus 2X is. So since y was the opposite side, right, x is the adjacent side, so x is going to be 50 cosine 34 degrees. Because we just do adjacent over hypotenuse. And so now when I plug it into my formula, D is going to be 1 minus 2 times 50, which is 100 cosine 34 degrees. So we actually now know how tall a ship has to be, right, to clear it. And we know the width of a ship. So a small ship, right, might be able to squeeze under the arm, right? And a really tall ship would have to go through the middle, but we'd have to make sure it's not too wide to fit through.
Wait, where'd you get 100 cosine 34?
Because 2 times 50 is 100. See, I plugged it in here? Yeah. Mm-hmm.
But that wouldn't multiply the angle?
Nope. The numbers on the outside do not affect the inside. So there was I know there was an Alex question that I went over with somebody the other day where cosine of 2 theta, right? If 2 theta is on the inside, it means you got to double the angle before you do the cosine, right? But if it's 2 times cosine theta, then you find cosine of the angle and then double the result, right? So just like with, even with logs, right? One's a coefficient, and one's inside the function. The only unique thing we had about logs was if you had a coefficient out front, you moved it inside and it became an exponent. It still didn't double the quantity inside, right? So 2 out front and 2 inside that means 2 different things. Yeah. All right, so the next thing that I want to talk about is looking at problems where we describe angles in terms of like angle of elevation and angle of depression. So the thing you want to make sure that you get down when you're labeling these angles is it sort of feels like you're supposed to have an angle inside the triangle, but sometimes we can describe problems where we're actually giving you an angle outside of the triangle, right? And then you have to make an adjustment to figure out what the angle inside. So when we're talking about angle of elevation, what we mean is your eye line, right, is straight ahead. And if we talk about the angle of elevation, you're looking up at something. So that means you have to look up to see the object, and there's the angle of elevation. So it's always between the horizontal and where you're looking up to. If we're talking about the angle of depression, well, you start with your straight eye line, and then you're looking down at something. So the angle of depression would look like that. Now there's another rule in geometry that some people remember, some people forget. But if you ever have 2 parallel lines, and then you draw a line across them, there's a rule that says the opposite interior angles are equal. Right? So remember that notation? So the angles with 1 tick are the same, the angles with 2 ticks are the same. But we can actually sometimes have that same angle measure repeated throughout the picture because of that rule. So that's another way that by giving you 1 angle measurement, we may have given you multiple angle measurements. You want to make sure you understand that. All right? Also, remember complementary angles add up to 90. So if two things form a right angle and you know one of the measures, well then 90 minus that angle is the other one. Right? That's one way you could move an angle inside the triangle. And then supplementary angles form a straight line. So these 2 angles are supplementary and they add up to 180. So if you knew that this was 30 degrees, then that has to be 150 degrees because they have to add up to 180. All right, so let's look at some examples involving elevation and depression. So we have a point 23.3 meters above ground level, and an observer measures an angle of depression of an object on the ground to be 50 degrees, and we want to determine the distance d in meters from the object to the point on the ground directly below the observer. So there's a lot of stuff. So what I like to do whenever you're elevated off the ground is I just like to imagine you're like standing on a building because it just kind of seems more relevant. So imagine, right, we got somebody hanging out on top of this building, and the building is 23.3 meters tall. And he's looking down on an object on the ground. So the horizontal distance out from the building is going to be like this, right? And his viewpoint, right, is down here. So, right, you can kind of see from where he's looking, we're just making sure that our right triangle is just to the top of the building. And what we want to know is how far away is the object from the base of the building, which is a point directly below him, okay? So in this case, they told us that the angle of depression was 50 degrees, so that means this angle is 50 degrees. See, that angle's outside your triangle. However, that dotted line is parallel to the base. So what you have here are 2 parallel lines with a line cutting across, so that means this angle is also 50 degrees. They're opposite interior angles. If you actually extended that dotted line out, you would see you've got this set up right here.
With the 50 on the top, make 40 and 50.
You could also say it's 40 on the inside and use that angle if you wanted. But it's just going to be opposite interior. Now the reason this is kind of important, what we're saying here is a person on top of the building had to look down 50 degrees to see the object on the ground. However, if I move the box to the top of the building and I put the guy where the box is, his angle of elevation to look at that object is 50 degrees because we drew a straight line. So if you change the perspective, right, the angle of depression becomes the angle of elevation and vice versa. All right. So if we want to find the base of the triangle, well, we know the opposite side. We're looking for the adjacent side. So opposite over adjacent, that's tangent. So we'll say, well, tangent of 50 degrees is 23.3 divided by x. So x is 23.3 divided by 50. That is your exact answer. What's 1 over tangent? Cotangent. So I could also say that it's 23.3 cotangent of 50 degrees. Those are equivalent. So what's the advantage of one over the other? Well, if you're typing this into a computer, it might just be easier to type cotangent than worry about a fraction, right? If you're actually calculating the value, well, then you want to leave it in tangent because your calculator only has a sine, cosine, and tangent button. Okay, so these are equivalent answers. Some people like to change it to simplify it down. Some people don't. I would accept either one, but just keep in mind that if you see an answer that doesn't look like your answer, could it be the reciprocal identity was used, right? To just string it all out in one line. Are we good? Okay. All right, so this next one, we have an airplane, right? And it's flying at an altitude of 40,000 feet. So altitude means vertical height above the ground. So when you're doing airplane problems, you have to make sure, because right, we're always going to be setting up a triangle, that you're putting the plane in the right position. So if the plane is taking off, right, the path of the plane would be the hypotenuse because it's going to be flying at an angle. Same thing if the plane is landing, right? But if it's flying at a specific altitude, then we assume that it's just flying a straight line path at that altitude. So it's flying, right, at a height of 40,000 feet. And it says, oh, sorry, I lost my thumb. Okay, here we go. So it says 1 minute later, right, the plane is, so as it's flying over here, right, it flies over an object on the ground. So this is at t equals 0. Then 1 minute later, so when t equals 1 minute, the angle of depression from the plane down to the object is 43 degrees. So this angle is 43 degrees. And we want to know what is the speed of the airplane to the nearest mile per hour. So if you ever get lost on things like this, use the units to your advantage, right? And everybody should know the units of speed because hopefully we've all at least ridden in a car, driven a car, right? We measure things in miles per hour. Miles is a unit of distance, hour is a unit of time. So the formula for speed is always distance over time. So this is why it's important to get the plane in the right place, because when you're calculating the distance, you want to make sure you're calculating the correct side of the triangle. So in our problem, the distance covered by the plane in 1 minute is the top of that triangle. So if I can find x, I can plug in my time of 1 minute and then I can calculate the speed. So x is the adjacent side to the angle, right? 40,000 is the opposite side. So we're going to use tangent. So tangent of 43 degrees is 40,000 over x. So x is 40,000 over tangent of 43 degrees. And this is in feet, because 40,000 was in feet. So the question says, give us the speed rounded to the nearest mile per hour. So the first thing I'm going to do is I'm going to plug my distance into the numerator. That's in feet. When I divide by 1, it just comes back as itself, but minutes, right, go into the denominator. So what we have is the speed in feet per minute. Now I need to convert this into miles per hour. So I don't expect you to have memorized how many feet are in a mile. Obviously, if you're doing stuff for homework, you can look it up, right? But on an exam, if we want you to do any strange unit conversion, I'd probably give you the conversion, with the exception of things you're supposed to know, like time. We just expect you to know the conversions for time. You have to know how many minutes are in an hour and seconds. So for this guy, right, there are 5,280 feet in 1 mile. So feet will cancel feet. And there are 60 minutes in 1 hour. So minutes cancel minutes. So what you're left with is 40,000 times 60 over 5,280 times tangent of 43 degrees. And I think this rounds to either 527 or 587 miles per hour. I did not bring my calculator with me. I did this problem today, but it's roughly, I think it might be 567 or 5, somebody working this out. Make sure your calculator's in degree mode if you try to calculate it. Anybody?
This says 487.
487, yeah. Just forgot the middle number. There we go. It's about 487 miles per hour. So airplanes, when you're dealing with airplane speed in miles per hour, it's always usually somewhere between about 300 and a little over 500. That's pretty standard answer. So if you were getting like 1,200 miles per hour, that's way too fast. And if you were getting like 20 miles an hour, that's way too slow. So that's a good legitimate speed range. So that's solid. All right, so let's do another one where the plane is taking off, okay? So now the plane is taking off at a 15-degree angle. So that means, right, the plane is flying along the hypotenuse of the right triangle. And we want to know, how long does it take for the plane to reach an altitude of 15,000 feet? We were given the speed of the plane as 150 feet per second. So this means when we calculate time, time's going to come out in seconds because it's going to come out in whatever unit of time the speed was in. So if speed, right, is distance over time, then time is going to be distance divided by speed. So if I can figure out how far the plane flew to get to 15,000 feet, then I can plug that in and divide it by the speed. So we'll call D the hypotenuse. And this is going to be opposite over hypotenuse, so we're going to use sine. So the sine of 15 degrees is 15,000 over D. So D is 15,000 over sine 15 degrees. So now to get the time, well, we're going to plug D into the numerator. Right, so there's D. When I divide a fraction by a constant, the constant ends up in the denominator. So my 150 is going to end up right there. So if you typed it all in and then hit divide, that's what would happen. And this works out to be about 367 seconds. And usually with time, right, if the unit of time comes out and that's not when I mean a reasonable number, if that doesn't have like a good reference, like you don't get on a plane and your pilot doesn't say, "Good morning, everyone, we're going to fly 3,287 minutes to our destination," right? Nobody would tell you that because we have no context for that. So usually what you do with time is you keep bumping up the units until it makes sense, okay? So if I bump this up to minutes, It works out to be 6.4 minutes. So I would stop there because you also don't want to go too far and say I have 0.13 of an hour. That doesn't mean anything to anybody either. So usually we adjust the units of time so it sounds reasonable. So when you get above 24 hours, right, then you start converting to days, right? When you get above 7 days, you convert to weeks. When you get above, so many weeks, we start converting to years or months. Usually we go from weeks to years because months can vary, right? So that makes sense? Okay. All right, so let's do the last one. So in this problem, right, we're at some point A that is 8.8 meters above level ground. So I'll put us on a building. And it says the angle of elevation to the top of a building is 35 degrees, and the angle of depression to the base of the building is 18 degrees. Approximate the height of the building. So what you want to kind of imagine here is we're in a city or just next to a tall building. And so we have a small little structure that has a height of 8.8 meters. And we have a much taller building next door. And so if you're standing from this position and you look to the top of the building, you have to look up at an angle of 35 degrees. But from that same position, if you look down to the base of the building, you have to look down 18 degrees. And what we want to know, right, is what the height of the entire building is. So if I extend this dotted line out, I actually have two right triangles. And if I can find the height of the upper triangle, right, which I'm going to call y, and I can find the height of the lower triangle, I just add them together. But what's the height of the lower triangle? 8.8. So the height of the building is 8.8 plus y. So now I just need to find y. So if I look in the upper triangle and I try to find y, I don't have a second side to use any of my trig functions, right? So my only options were sine, because it's the opposite side, or tangent, because both of those involve opposite. However, the two triangles share this side right here. So let's call that guy D. So if I go into the bottom triangle and I calculate D, I can then use D to calculate y in the upper triangle. So in the bottom triangle, this is opposite over adjacent. So tangent of 18 degrees is 8.8 divided by D. That means D is 8.8 divided by tangent of 18. In the upper triangle, we have an angle of 35 degrees. So tangent of 35 is y over D. So y is D times tangent of 35. So now I can plug in what D is. And now I know the height of y. So I'm almost done because the goal was to find the height of the building. So the height of the building is 8.8 plus y, which is 8.8 tan 35 divided by tan of 18. So if you notice the pattern of what we were doing here in all of these problems, we drew the picture, we figured out the quantity we were looking for, and we wrote a formula for that. Then we went piece by piece and just solved for the things that we were missing. So the formula we generate initially actually tells us the path we need to take to get to the answer, right? But hopefully you can see that just learning what these terms mean and learning what these words mean make drawing the picture much easier. And once the picture's in front of you, the math really wasn't that terrible. It's just which trig function do I use? Am I adding these two sides together? but it's just a geometrical, like visual representation. And so that's how a lot of the word problems in this section are gonna work. So get really, really good at drawing the pictures. And you have your book that's available on Alex, and I really recommend finding some of the word problems in the book to practice doing this. If the picture is provided, pay attention to the verbiage in the problem and notice how those words correlate to those positions, because that way if you ever have to draw it on your own, you can do it.